Okay, so let's start the session now. So before to start, uh, how did you feel the previous weeks? Anyone?
What did you say, sir?
Previous week, like week 1 and 2, how was that? Are you able to understand?
So in maths too, there are frequently understanding the basic new terms and other terms. So it for me, I'm little bit confused about the terms basis, change of basis, and the canonical basis,
Okay,
span, right?
okay, okay. So today we'll see week 3 is also exactly that. So today we'll see, and also I will try to make a note on that how we can distinguish properly. So that's good thing that it's make confusion more and more when we listen the more term is span basis, and we'll try to rectify this. So it will be a proper arrange so that able to get it, because today's topic is again related to the vector space basis. These all things will come again, but we are going to see it for Rn. Rn means previously we have seen till week, sorry, till R2 means till R2 only means R2 we have seen. But now we are going to say for Rn for more general case. But the terms are not going to be changed. Okay, the terms are not going to be changed. There is no change, even wording anything concept, no change you will see. Okay, only so that's why I will try to emphasis on to make a distinguish between these terms so that all of you are able to understand properly. Okay, any other difficulty anyone is facing? That would be good to know that while discussing that I will try to make a proper uh, difference in those words, means at least
Mainly in change of basis only.
okay, change of basis.
Also, sir,
Okay,
that matrix question where we have to change basis in matrix.
in matrix form, yes. So that is the week two, no? That is of for in the matrix case, yeah, it is done for in week two. It is done in week two. We'll see it where it is. Okay. Is there any background noise from my side? No. Fine.
Very little,
Sorry.
not much.
Okay. So how many of you gone through with the week three content? At least half of the, because today we'll discuss only half of the content. Yeah, good to have at least, so that that we can ask doubt. No, knowing to be good, the doubt should be come from student side, so that if whatever I will discuss, that may not be more convenient as you are looking that topic. If you ask that in those perspective, if we discuss that, that would be good. Okay. So I hope my screen is visible. So topics in week 3 is again, if you see it, vector space in Rn, a span of vectors, span memberships, and linearly independence and dependence, spanning set and basis. See, the terms are the same. I will show you in the week 2 also. Elimination, spanning sets, span and dimension, and the example on it, span and dimension both only. So see the terms you calculate. So collect these terms. The terms are vector space, span, basis, linearly independent, dependent. Same terms we just now seen in week 1. Vector space, linear combination, span, same subspace is also, you'll see linearly independent, dependent, basis, dimension, same thing. Same terms are going to be, we'll see there. So this week 1 we have seen for R2C. Here it is written R2. Here is R2. Everywhere you will see for R2. But now in week 3 we'll see. See now, if you see here is the dimension or any case, general case for this is here. This is for matrices M cross N, or maybe here you can see for Rn, vector space in Rn, first lecture itself. So everything is going to be span membership. Everything is same. So let's discuss that. So we'll discuss more on question wise. So vector space we have seen. So the definition of vector space we have seen last time. So vector space we have seen even R2 or even vector space V. We have seen where we have previously seen for R2. Now we are going to see for Rn. So I will relate with the each time with the previous time whatever we discussed. So there we have seen some set of rules, some 8 rules we have seen. Where the first is we have seen the closed. So I am using the word which I have discussed last time, the closed word, closed under addition. What it means that it means that I will take. So even see, now if you forget for the time like this, okay, and I'm saying for V only, okay, V means any general case, means this will come under R2 and R3, but the terms whatever I will write now, everything is going to be same. Everything is going to be same. Even whatever we have seen for R2, this is going to be exactly same in Rn. But difference in R2 and Rn, what is the difference? First, let's see that. Rn means, let's say here is in place of Rn, let me write 4, R4 or R3. Okay, R4, R5. This will go any. So I'm writing, let's say, for R4. So this is R4. Okay, any of the number I can take, more than 2. Okay, so R2 here, R2 means the terms, means arguments, or we have seen the coordinates, number of coordinates here. You will see here A and B kind of means here we will see, if I will write here in the vector wise, let's say here this case A and B, or 3 5 4 5. We have seen this in R2. These vectors, these are vectors. Now I will use the word vectors. These are in R2. What it means by R4 or R3? Let me write these two also, R3 and R4. So here in R3 you will see the 3 coordinates A, B and C. In if I vector wise I will write both are the notation as I am. So A, B, C. For example, here it is 3, 5, or even any number. Okay? Or here it is any of the 10, 12, 1000. So this is in R3. So what is you are looking? One extra thing is added in R. In place of R2, you are looking some extra coordinate. This is still R2 it is, but in R3 this is. Similarly, R4 is going to be the same. A, B, C. One extra will be more than 3 it is. So then how many dimension? Means here it is how many number? 4 is written, the 4 coordinates will come. 4 arguments will be there. A, B, C. Let's say D. Or if I will write in A, B, C. For example, here 3, 5, 6, 8. So simple. It is just expansion. See, it is a kind of expansion we are doing. Previously we have seen for R2. Now just extra coordinate added, or now it will become R4, R3. That is the meaning here. If I will see geometrically, so geometrically it is till R2 we are able to see as the two lines, this R and this R. Only this, and the vector, if I will represent here 3 and 5, so somewhere 3 and 5 is here, and the vector here it is this one. This is R2, means we are able to draw it. And exactly this is coordinate system, you have seen the coordinate. This is exactly R2 is very similar to that. But in R3 now, in R3 what is going to be? R3 is going to be one line is there, second line is there, and let's say there is a height. What is there is height, means there is a, suppose this is a plane, this is a paper where I'm writing. Now suppose there is a one height I kept here. So to represent properly the height, generally represented like this. Suppose this is your height, so this is your R, this is your R, and this is your height 1 R, just height. From the pen you just make the above your, sorry, from the paper, or yeah, from the paper you just make the above. Or you can see your room, or you are in the space, so you can see of your room the corner side, three lines are there, the corner of any of the top corner, the lowest most corner. If you see three lines, three edges are there, so three edges you can see the similar way. So here it is. This is your R3. Now 3 R uses, right? 1, 2, 3. So that way you can see this is your R3. R4. R4 we cannot visualize. So I am not able to draw it. So till R3 we are able to visualize. So I can do it, but not more than that. So I'm not, now next line is where I will draw so that it will become R4. I don't know even so, see, we cannot visualize it. So that's why it's very difficult to write also. Not very difficult, even I cannot even write. So I can give the example. What is the 4 dimension thing? If you see what is the 4 dimension, generally, if you see one like you are running on the ground, okay, you are running on a ground. So you are running on R3, means the anything you are doing is R3, the space is R3. But suppose for the time being, one extra dimension is I am adding as a time, that in 1 minute you are running this much. No, in 1 minute you are running 100 meter or 200 meter, whatever. So running is one place where your wherever you are the space you're living, that is one thing. But time I have added in that. Time I added. That is, in I have added in one time. Means in 1 minute you are running that much. So you can see that fourth dimension you can think as a time. So we cannot visualize, but we can orally do, right? Similarly, I can add one more thing, some any dimension I can use, like the way it is. Time is one thing is there, or maybe anyone can give any example also to make the more dimension 5, 6. Anyone have any idea? All of you are able to get it. What is mean of I mean to say the R4?
Yes.
So anyone can give a what is R5? A very distinguished number you can add so that it will be independently you can say. Anyone? No?
We can
Even I'm
take
not.
any
Hmm.
number like 1, 2, 3, 4, 5 also.
So, but if you try to relate with that person, what you can say, so that we means understanding, make the better understanding. Like I added our time in that, so that he is running in the space, but in 1 minute or 1 hour or an infinite hour he is running as a 100 meter. So one dimension address. Similarly means let's forget it now. Means you can leave for the 5 dimension. But this is how the dimension increases. That's how the number means. Now, if you see, if you try to from the field of the corner, if a person is here, or even let's say plane in R2 is more better visualization. This is the field, suppose. So uh, from the field of the corner he is here, so to represent it in the reference of field, this much from this side and this from this edge of the field, and he is there. So if you see the proper direction from the reference, you are taking the corner as a origin. So this is the person here in a vector dimension. And if you try to add the height of the person, you can add it, so that will become 3D. It will become 3D. So this is how. So to represent it, to represent the vector wise, suppose this is 5, this is the 3, and this is 5. Okay. So with respect to without adding the height, this is at the field the vector related to that person is 3, 5. If you are including in height of the person also, so this is going to be 3, 5, and suppose his height is 5 feet or maybe 5.5 feet. So this is how it is. You can relate it. So R2, R3, this is how it terms. So we don't need even these things. We just need to know the more algebraic way. Like this is the case. I'm representing like this. This is how it is. And more algebra will try to do. So algebra means we'll try to do basis, we'll try to find the span. These all will do. This is the more pictorial representation, and this much is enough to know what is R2, R3, and Rn anything. So I hope it is very much clear what is R3 and R4. So let's back to our vector space now. So previously we have seen the closed under addition. Okay. So I am two vector I am taking. Let's say V1 and V2. Okay. So this could be anything now. In place of now writing R2, I can write now. Let's say this is either R2 or R3 or R4 or any general case. It is the all definitions are going to be same. Whatever I will write the condition here, all are going to be same. So Rn. So closed under addition. What it means that when I am adding these two, it will be belongs to the this P P. Okay. Let's say the closed under closed. The second exempt is closed under multiplication. Okay. What it means that the dot is there, and I am taking is any scalar, and I am multiplying. We have seen this last time how we are doing this, are multiplied, added vector, is that belong to or not. While discussing the subspace, I discussed this. So try to relate it, because now I will go very fast to discuss this or vector space. I will more focus on basis and dimension. Okay. So this will belongs to the, okay. Similarly, there would be a zero vector 0, 0. We have seen, right? For R3, this will be 3 0. Okay. For R4, this could be 4 zeros. Okay. For R5, that many, how many Rn is going to be, that many zero would be there. So zero vector would be there. So I am writing as a zero, just zero. Zero could be any two-dimensional, three-dimensional, four-dimensional, okay, anything. There would be a zero, so that when I will add with that at V1, it will be give V1. And there is a inverse of it. What is the inverse? Means there could be a V, let's say V1 prime. Okay. When I will add in V1, it will give zero vector. What it means that V1 is nothing but your V1 prime is your minus V1, minus vector. For example, let's say I have 3, 5. So inverse of that vector is minus 3 and minus 5. See how it is when I will add, it will add like this coordinate wise. So this will be 3 minus 3 and plus 5 minus 5, which is 0 comma 0. We have seen last time. So there is the inverse of it. Similarly, all other alpha time V1 distributive. This is a distributive alpha V1 plus alpha V2. 1, that 1 scalar 1 is there. No? V1 is equal to just V1. So these are the exams will know. The associativity law V1, V2, and V3. That is, I'm adding, so you can you take any of the association. Yeah, this is how many things are there? One, two, three, 4, 5, 6, 7. One more is there. Yeah, I think what is the left now? Next is I am taking two scalar here, alpha and beta. When I am multiplying with the v1, it will be just distribute you with respect to the scalar also. So scalar is now, hope you understand. I am saying the scalar means your real number. You are taking your scalar means 1, 2, 3, 5. These are the vectors are the coordinate wise. These are the vectors. So 8 axioms. These all axioms will be followed by either R2, R3. So means this will make a sense. This will make a space in the case of it. Okay. This is how it is. So just to know it, there is no one is going to ask related to that. The question would be asked to say about the subspace. To say about the subspace. Subspace. So we have seen the subspace also last time, very detailed. We have discussed that. S1. No, S1 is going to be some set of V. Okay, V means, let's say I'm saying R3. So for example, I'm making here, let's say I'm making a subspace X, Y, and Z. So subset is, first of all, it is going to be subset, totally fine. Now, X plus Y plus Z is equal to 1. This is a subset of R3. Okay. Is this becoming subspace or not? So please let me know what are the condition I have to check here. Anyone remember to check that is this a subspace or not?
So
Anyone
close
remember
under
that?
addition and it contains zero vector or
Hmm?
I think multiplication also.
Multiplication. Yes. Three condition we have to check it. Even I said two also enough. So even the two also enough. These two.
Sir,
Zero
if
is zero
addition
vector.
and zero vector contains, then it should be a subspace,
Uh,
right?
no addition. No, only that these two. Closed under addition, closed under multiplication is suffices. Zero vector is not needed. It will be. It is already in that here in addition part. It is going to be already in that in addition. Only suffices if you check these two conditions. Closed under these two. If you want to add, you add your rule, but it's enough. No need of it. If you are making a third rule, let's I'm adding. If you are remembering with that, let's add this. These three rules you can follow. If it is following, you can do that. So these three rules make a mix. If you have a subset, it will make that subset as a subspace. Okay. So is this subset is subspace? Anyone? Is this a
No,
subspace?
No, sir, it's not.
Why it is?
because it won't follow the scaling rule.
It will don't. Yeah, even any very simply. I said third rule. Let's add that zero. Zero is in that set. Yes, one. Zero vector is in that yes one set.
No,
No.
No, right? If you say yes, let's say I'm saying the zero vector is there. Okay, totally fine. Zero zero I'm taking. Let's add zero zero plus zero zero. Will I get one? No, right? So it is not. So zero is not in that. Zero vector is not in the set. Yes, one. So simply you can from here you can say. Even you can check the additive closed under addition also very easily. You can closed under addition, closed addition or multiplication. It will all deny. It will not follow these all rules. So this is not a subspace. So with a very simple trick, if you are, let's add for the time being. If you said so, I am adding the three rules. Let's say closed. It should be closed under addition, closed under multiplication, and zero should be there. Okay. and zero vector now. So very simply with the third rule you can say, okay, zero vector is not in the set, so it is not a subspace. So this is all about the subspace thing. Let me see anything I'm missing. I don't think of this first lecture I'm missing. I will try to cover uh, how many lectures are there. Half of the lectures I will try to cover. So these are just examples. So 9 lectures are there. It's depend on the topic wise also. I will try to cover basis. I will discuss basis and dimension. I will discuss later. I will try to cover till span only, linearly independent and dependent span. Three terms I will cover. Basis and dimension will discuss in the next session. So this is Rn. Many of you have doubt what is Cn. I am not discussing about Cn. Okay, so I will discuss that also today. Last time I didn't discuss, and that is also not needed. Okay, we'll play on only complex number. Sorry, real number. So to know it for yourself, Rn is there. I will tell you what is that. See now the professor is now moving. What is the Cn? So if you have a doubt with, okay, let me. Whatever. Okay, let me first fix it. Uh, so how many of you, whatever I am discussing here, and with the term you are looking the lecture, is there any remaining terms or you are facing the difficulty? No. So let's
No, sir.
some more terms are here. Not more terms are there. Only the Fn is there. What it means? See, Rn is there. Common notations. So see, what is he saying? Fn notate. The common notation is place of Rn. We can notate as a Fn also. So don't be fear with the what is Fn, what is Rn. It's okay. So for this label, you should to know it. I am writing Rn. It means that your numbers are coming all are coordinates are coming all are real. Fn, Fn is notation for what general case or more general case means the general notation, common notation it is just notation, nothing more. Because what is this Fn? There is a broader case of field word is there, field. So the field F is taken from there. So that is not needed here. So for yourself to understand, this is just a notation. So you can even I can say that Rn and Fn, the notation wise same. So nothing is difference here. No more difference. Okay. So now everything if you see it here all are a scalar. Okay, I will discuss the linear combination now. So vector space I hope you understood. Linear combination I will discuss now. Span is already professor is discussing with him that. Okay, he is just making a summary I think. Okay. So before so till here vector spaces at least for understanding purpose all of you is clear with that. The 8 axioms are there, list of 8 axioms. All are still doubt. So use cases you will see what the question would be asked only on the subspace. So only three rules are important, but topmost axioms. Okay. Now let's discuss the combination. So we have, again I will relate each time. Okay, each time I will relate with the previous time. Okay, so I will make a proper node. Okay, basis dimension span. So maybe I will maybe here I will make a difference till span and dimension. In the next lecture I will make the differences between change of basis, span and dimension. So let's discuss the linear combination now. So in R2, the first of all, what is a linear combination? We have discussed a lot. What is linear meaning? Linear meaning, I will just try to recall it very short. First, we have seen a function of case ax plus b. Okay, and then we have seen the more case, the more general case fx is equal to x square plus bx plus c. So such kind of function called linear function. Why? The reason is here the the degree of the function here is these are called the terms. The degree of each term is at most one. Here is the degree of, here the first term is one. So you can see the degree of the first, here it is one. Even if you have doubt, here the degree, or here is c, here the degree of this term is 2, here the degree is term is 1, here is the degree, you can say 0. For the constant you can say 0. Here degree is 1 2, sorry, 0 1 2, 0 1 2. So if you say the degree of the function here is 2, so if the degree is 2, then it is not a linear function. So degree is 1. When the degree is at most 1, you can say even the constant you cannot include. If the degree of the function is 1, you can say the linear function. For example, let's say ax plus by. Here it is, this function is two variable function and the degree of each term is 1. So that is the meaning of the linear word is came from there. So linear combination is, I'm taking the combination. Okay, so let's say combination of the vectors, linear combination. Okay, how it is taken, see it here. So let's say I am taking the vectors. So let's say I'm taking, I will we are going to discuss for Rn. So let's say I'm taking the vector space R3 and vector I am taking here, let's say 1 2 3 and 4 5 6. Two vector I took here. Let's say this is v1 and this is v2. Even one more vector I am taking here, 6 7 and 8. Even differently, 1 1 1. Three vectors I took here. Now linear combination. Anyone have remember what is a linear combination? Can you tell me the two R2 case?
The scaling and the like addition and scaling.
Adding, yeah, scaling and addition. That's the proper word. Yes, that's the good thing. Just scaling up means here taking the linear combination. I'm taking some scalar. Okay, I scaled up the vector v1, some any scalar. Similarly, I scaled up the vector second vector, okay, and I added here. Similarly, the third one here it is. Let's say I'm taking gamma here. So this is the notation of gamma and degree. So such kind of combination you can say the linear combination means scaling up and adding the vectors. Even though if you have a single vector, just a single vector, let's say v1, this is also a linear combination. How it is? This is a linear combination. If you want to see it visualization, here is one scalar one dot is going to be one, and you can say the 0 0. If it is in R3, so 0 0 0. So this is also a linear combination. So single vector is also a linear combination. You can thought if you are thinking it as a linear combination case. This is also a simple linear combination v1 plus v2 plus v3, where the alpha is 1, beta is 1, gamma is 1. All are 1. So simply this is a linear combination. So linear combination is nothing but if you are just multiplying with some scalar or scaling some scalar. So multiplying means scaling of the scalar, sorry, vector and adding them. This is called just a linear combination. So we have discussed this very detailed. So let me take. So I'm now making the question here properly. So even here. So the question is, let's say I have this 1 0 minus 1. Okay. I have this vector v4. Okay. So is this vector a linear combination of v1, v2, and v3? The same question I have asked. See why I am making the same thing, because so that this is the very similar question I have asked in while discussing the week one. What is the new thing? New thing is I just added the extra coordinate there. So is this vector is linear combination of v4 is linear combination of v1, v2, v3?
We have to solve linear equation.
Yeah, we have to solve linear equation. Then we'll get. So here previously we have very simple equation. We have done this. How we check that? How we can check? So the simple way I will tell you two ways also. Okay. So to saying that is this a linear combination of these all, or let's say v4 is a linear combination of this v1, v2, v3 means some alpha times some scalar. Is there any scalar when I will add here beta time v2 plus gamma time v3? When I am doing such thing, I am able to such alpha, beta, gamma. Okay, so that we are able to obtain v4. This is the question here. So just a minute. Now let me see it once. Just a minute. So I will discuss the I will tell you two ways. Okay, so first of all, I will discuss one way, which is a very simple. Uh, The way it is will follow. It means here writing 1 0 minus 1 is equal to some alpha time the v1 vector, which is 1 2 3, plus some beta time 4 5 6, and some gamma time 1 1 1. So we will get this. Once we got this, so means here if we'll try to solve this, see this is a vector type equation. No? This is a vector type equation, but we can convert this as a uh, system of linear equation. Very simply, we have seen last time. So you can multiply here. You can make a single vector. No? You can get a single vector here. So like here, if you do it here, some uh, 2 time v1 plus 3 time v2 plus 4 time v3. So it means 2 time 1 2 3 plus 3 time 4 5 6 plus 4 time 1 1 1. Okay, so by adding them you will get a single vector. How you can add? So multiplication is the same coordinate wise last time as it is, the very similar. This is 2, this is 4, and this is 6, and here is 12 15 and 18, and here is 4 4 4. So now add them. So coordinate wise addition will also done. So 2 plus 12 plus 4, you can add this all. 2 12 14. Similarly, 4 plus 15 plus 4, 6 plus 18 plus 4. Like this addition will do, and you will get a single vector. So this is 12 and 18, and this is 23, and this is 24, 28. So see, you got a single vector. Similarly, we can get here the vector alpha. Okay, alpha plus 4 beta plus gamma, and 2 alpha plus 5 beta plus gamma, and 3 alpha plus 6 beta plus gamma. Okay. Now you got a single vector. The two vectors are equal. It means that alpha plus 4 beta plus gamma is equal to 1. 2 alpha plus 5 beta plus gamma is equal to 0. And 3 alpha plus 6 beta and yeah, plus gamma is equal to minus 1. See, we got a system of linear equation. Here the variables are not x, y, z. Here the variables are alpha, beta, and gamma. And if this system have solution, if it have, then means what it means, that you are able to some alpha value, you are able to get some alpha beta value, you are able to get some gamma value. Means you are able to get a linear combination such that you are able to obtain this. If this system don't have, this system haven't solution, this system don't have solution, in that case, in that case if the system don't have solution, so there is so this vector is not the linear combination of these one. Okay. So this is one way, this is one way. So okay, this is one method, but I want to check. So second method I want to discuss. So second method is that professor, whatever the professor is discussing, elimination method. Okay, elimination method. How he is doing, how he is eliminating. Anyone remember that method? How we will do that?
This element,
Making the column wise at 0 after one row. The
Hmm.
next column will be 0. All the points till we get the last row is equals to 0.
Yeah, that is what it is. So means here eliminating means here is professor doing no this how he is doing like let's say he is eliminating between the vector u and v. So how he is making, he is assuming any one of the is non-zero, okay, some b by alpha 1. What he is doing, he tried to make the, if here is your u and below of it w is, he's tried to make it 0. So he is not discussing in the matrix wise case, he's just discussing orally, how we can make, how we can do that, how we can arrange that, so that it will be. So if you try to do in arrange wise in the matrix form, you know what is a matrix? Matrix is just arranged form, means you can say array, arranged array, or you can say just say the array. Matrix is you are arrange the number properly, that's all it is. So I will discuss that method, okay. So exactly whatever the method is there, the elimination method is, that is the only case. Because here now we'll see here whatever the examples now matrix case, we'll discuss that. That is the, see, matrix dimension. So I will discuss more on. So here even let's discuss a bit here also with the case of knowing a simple method, okay, how it is. So the way it is, the second method is, you can check, you can take the vectors here first. Let me take the vectors. Let's say any of the vector, you can take the first vector as it is. So here let me, I'm taking the first vector, I'm writing as a row wise, 1 2 3. This is my v1, right? This is my v1, I just wrote row wise. The second vector is v2, which is 4 5 and 6, and the third vector is 1 1 1, right? And the fourth vector is, so I, so this these three we have, these the vectors I have, these are the vectors I have, three vectors I have. I want to check the fourth one is a linear combination, means here the linear combination or not. So what you can do, you can now write in the last the fourth vector 1 0 minus 1. I want to check the v4 is the linear combination of these three or not. So this is how you can write easily. And you can any of the shuffle, you want to shuffle it, you can easily, for the convenient way I can shuffle. Like let's say I'm making the shuffling is that this one, I'm writing v3 first, 1 1 1, and then v2 1 2 3, and then sorry, v1 and then v2 4 5 6. So you can shuffle it, even you can shuffle the fourth one also, but to way to understand it, you can do like this. So see, it is 1 0 1. So either any of the way I can write it. This is our v1 and this is v2 and this is my v4.
So this is
So
called row swapping, right?
no, I not doing row. Yeah, this is called row swapping. Yes, this is row swapping.
You have done the row 3 to row 2.
Yeah, I just bit change here, interchange between a row one and a row three. So this is what I did. So it doesn't matter. However you want to write, you can write. Even you are writing like this, you can proceed. I just row swapping is like this. Sorry, R3. So row 3 I interchange. This is the sign of swapping or interchanging the row. Okay. Now let's proceed with the elimination. How he is doing dividing and adding. So what he is doing there. So you can now below try to make it below as 0, or let's make it 0. So here is 1 1 1. So what I am doing the next operation, to make it below 0, I can subtract row 2. From row 2 I can subtract row 1. Even you can say these are the row 1. Even if you have uh, even let's say I originally I wrote, so here is, this is row 1, this is row 2, this is row 3, and this is row 4. These are the rows, right? These are the rows. So I interchange here row 1 and row 2. This is the operation I performed there. This operation row 1 and row 2. If you can understand, like you can do so anything you can do. I mean to say, see, I said you can write like this, or let's write this case. Okay, let's write this case and then do the further operations, interchanging the rows. Okay. So why I am doing so that here the writing one is makes easier. Why I am doing this? The question is why you are doing this. Question is, if here is 1 1, so making the below 0 is our reduce effort. It will reduce our effort, make the easier calculation. That's why doing the row interchange is like here is 1 1, so that's why I interchanged row 3 and row 4. Now I am subtracting from row to row 1. So let's see here what is happening. So subtracting means here just subtracting these numbers. So here it is just going to be uh, 0, and this is just 1, and this is 2. Okay. And here is also perform. Also you can perform the more extra after doing this. Okay, you can write the all here 5 6 7 1 0 minus 1. Okay. Or simultaneously you can do also, means here also you can do r3 minus r1. Okay, and then accordingly you can write the row 3 if you want. Okay, so you can write or in the next step you can write r3 minus r1. So here is 1 1 1 and 0 1 2, and here is now. So okay, so here is
Sir,
not only I have to
R3
perform
minus 4R1.
4 r1, not only have to do just r1, multiply with the 4. Every term will be multiplied with the, here is every this first row you have to multiply with 4 and then subtract. So how, see how it is performed there. So here it is 4 minus 4. Okay, and it is 5 minus this one, and then 4 times again it is 5 minus 4, and 6 minus 4 times 1 4, and this is what it is happening, and 1 0 minus 1. So you will get here 0, and here you will get 1, and here you will get. See, now observing thing is that, see, these two are exactly same. These two are exactly same. So you can now do the next step as here row 2 minus sorry, row 3 minus row 2. So if you do that, you will get here 1 1 1 0 1 2 and 0 0 0 all. See, I suddenly did, so I should to make it his 0. So let's proceed first that. Okay, let's proceed first that, then I can next in the next step I can. So here now, what you can do, from row 4 you can subtract row 1. So you will get here 1 1 1 0 1 2 0 1 2, and so even additionally I can perform here. Let me perform also along with that row 3 minus row 2. I can perform independently. Okay, but where you are changing, first change that, then perform. Okay, if whatever the, see, these two are a totally independent operation, right? So you can perform. Okay? These two are totally independent of things are there, so you can perform. So that means here you can make it all here 0 0 0, and now here it is your 0, it will be, here is minus 1, and here is minus 2. Next is what we can do.
Sir, from this we can just simply tell.
From here, can we tell something?
Yeah, it is linearly dependent.
From here, can we say something?
It is.
No. Why the last row is not completely zero? It is the last row is 0 minus 1 minus 2. It should be 0. Then we can say this
Then
is
we can say,
completely.
if it is
Yeah.
becoming 0, so let's reform that, try to make it 0. Let's, till now here is not, this is inconclusive. So what we can do from here? From here, we can perform in R4. I can add R2. If I in R4, I will add R2. So it will give some better understanding. So this is going to be 0, 1, 2. Okay, and this is the third vector is already here. What it means that I will explain that also. What it means that I will tell you in the terms of independent and independent. Okay, so it is telling more things. Okay, so let's perform it here. And this is here once you add here. So this is already 0, and this is 0, and this is 0. Okay, is this correct? Yeah, it is correct. No, yes. Yeah, it is correctly done. No, yeah, this is just
Sir,
minor part.
from
Yeah. So yeah, we
sir,
once
I
we
R3 totally zero. Why? There is in before R3 R4 minus R1 it is 0 1 2, and now it is after operation 0 0 0
no, here
R3.
is previously I have did. Here is I perform no operation 1. Both are
Okay,
same. So
two
here is
operation
I
at the same time.
at the same time. That is what I am saying. I can perform two operation times simultaneously, but the see the operation differences. Both are totally independent. They are not affecting to each other. So we can perform. That is the what I mean to say. Two operations I can do simultaneously, but they should not affect to each other. So that's why here becomes 0. So see now the thing is that this fourth row here is the V4. This is our V3. This is our V2, and this is oh sorry, I slightly interchange no. So this is V3, V1, and V2. So here is this is my V3, this is my V1, and this is my V2, and this is my V4 already. I that's why I kept V4 in the last. What it means that what it says that yes, V4 is a linear combination of these V1, V2, and V3. This is the meaning of it. This is the meaning of you have done the solving the system of linear equation. I think if you have solved in maths one, I think so. Where all of you studied solving the system of linear equation in maths one, or here
Yes, sir.
is
Yes.
still remain to see in maths one. All of you see. Okay, yeah. So that's a good thing. So here is if you solve this in this solution also while solving the with the whatever you learn, the same thing you will obtain. Same thing exactly. The process is going to be same. So see what it tells. The R4 are this vector. This is my vector. Some operation I did, and it becomes 0. So this tells you that yes, V4 is linear combination of V1, V2, and V3. Okay, this is how you can tell. So this is the second method. You can take it to get it is that linear combination of these three are. Or you can solve the system of linear equation. So what is happening here? If you try to solve it, you will follow the same procedure. There also you have used to do this. Hope you remember that. So I'm saying the second method. It is actually the first method itself, but writing the way it is slightly different. That's why I'm saying it as a second method.
Sir, can we do either method? The first
Any of
one
the method you can follow.
solving both
Yeah,
will be
any of
correct,
the
right?
method you can follow. Yeah, both are correct. Either you can solve a solution exists, you can say it is a linear combination,
Because
or you can
for me, I solve the linear equation too frequently, but this is too messy to do operations to determine that it should be not dependent with the other row or column. That's why.
okay. So you can perform any, you can do any of the equation, and here, yeah, you have to write. You have to say that observe. Finally, you have to add the final thing. You cannot directly say. So you can say observe. While if it is a subjective, you have to write observe that from this step. You can say observe that after doing okay these operations, okay, we got v4, uh, which is row 4, even whatever the word you can say, or from the you can even v4 or whatever the thing. Observe that after doing the operation, this v4, we got v4, or sorry, in place of here r4 become r4, sorry, not r4, row 4. Row 4 is 0. That means that means v4 is a linear combination of v1, v2, v3. Some word, if you add it, try to observe. Means here is from observation we are doing. No? It tells you from the observation. It tells you yes, this is nothing but. So what it means that these operations, what it tells, these operations, this is nothing but just these vectors are nothing but your, sorry, these rows are your vectors. No? These rows are your vectors. You are doing something, you are adding, multiplying, scaling, you are what you are doing, some linear combination of the vector, this one. So you are doing nothing. Here is I change the word r, but here in place of writing r, you can write here right side v1, v2, v3, whatever the convenient way you can write it. The main thing is that you are understanding or not the operations here. Means you are understanding or not the concept here. So from the observation, you can say yes, observe it that yes, these vectors are making the linear combination of v1, v2, v3, or v4 is a vector linear combination of v1, v2, v3. So is this clear?
Yes, sir.
Yes, anyone want to listen? Okay. So this is how you can do the linear combination, and this is the meaning of, this is the concept of linear combination. Okay. Just a minute. Okay. So in the elimination method, that is what the professor is doing. What is the professor is doing? If you see it here, I slightly change here. Otherwise, in place of writing r, okay, here is r2 and r1. In place of writing r, I can write here the same thing, right? What I am doing here, from v3, I am subtracting what? The row 3, I am subtracting row 1. So here is v1 subtracting v1, v3 minus v1. This is what it's doing. Here is what we are doing. Here is uh, v2, v2 minus 4v1. That is what, right? Here is yeah. This is our v2. R3 is v3. So here v2 minus 4v1. This is what it's happening. So vector wise you can see, or this is what the enumeration method is you are doing. Here is corresponding that you can write. No. Sorry. Here is, I'm saying this is V1 is R1. Here is, so let me properly write here. Here is what we are doing. We changed. Here is each time row is actually here is if we make it to the proper thing here. So this is going to be, I am interchanging V row one and sorry V1 and V1 and V3. Yes, V1 and V3. And here is whatever the things are doing, you can accordingly write. Actually I wrote this R1 and R2 according to this matrix. Okay, here is what I'm doing according to this matrix, so that's why it's look like different, but same thing you are doing. Are you able to? I just wrote R1 and R2 with respect to this matrix, row and R2 with respect to this matrix. You want to fix it here, you can fix with the, so that's why writing V1, V2, V3 first write, and then in place of, you can make it as a row 1, row 2, row 3, and according to that you can understand. Okay, this is how it's a way to do. So the professional way is doing that. First write the rows, first write the vectors. Okay, now do the operations understanding your way, that okay, I just wrote these vectors here, but now row 2 minus interchange row 3 minus row 1, and then matrix you got, then other operations you perform according to the row and row 2. So you can follow that. Okay, so but yeah, I am explaining you, that's why I am writing here the vectors. See what I am doing with respect to the vector means, here the elimination method is nothing but we perform these all in the matrix form, in the more arranged form.
Sir,
Yes.
like if we make any one row 0 and then we'll change it to the last one, then we can also say na ki that it is dependent.
Yeah, so I will tell you with the dependent case.
Okay, sir.
Dependent case here is to understand that this is a linear combination or not, so that's why I didn't replace, I didn't, sorry, I didn't interchange the R4. Interchange with these three. I didn't change this V4 because it will make a messy. Okay, I'm not able. Then if you interchange this one also here, if you interchange this somewhere to other place, so I will not able to catch it. So that's why in the last I kept that okay, this is the reserve, or this is the reserve way for to understand. Oh, sorry, this is the reserve place for the vector where I'm checking this is a linear combination now. In the dependent and independent, I will mix up. Even you can see there what is going to be happen now. Interchange any row, any column. Sorry, not column. Sorry, interchange any row or do the operation with respect to the rows.
But sir, the last matrix we get, we can clearly say that this is a dependent vector, right?
This is what the dependent linear
So
combination or
basically, you are
dependent now.
telling the different case about the dependent and independent and about this linear combination. So what is the
Linear
basic difference
combination.
between that?
Yeah, this is the basic difference. See, linear combination is what, if you, I will tell you now. So you know that linearly independent dependent, so what it means, that it means that it what it says, that these vectors are linearly dependent. That is what it's happening, right? These vector v1, v2, v3 and v4 are linearly dependent. Why? The reason is they are able to generate the other vector. The v4 is you are writing able, you are able to write v4 as the linear combination of others. What is the meaning of dependent? So this is what it's happening. So exactly the same thing is, yeah, whatever you are saying, that is true. Yeah, this is what you can say, the v4 is dependent on v1, v2, v3.
And so without even doing V4 as 0, 0, we can say it is dependent in the earlier case also, right?
Yes.
Where the R3 became 0.
Yes. Yes.
Okay, sir.
So means here the method is, so to check the method is simply, if you want, you can follow this method to solve that. Okay, is V4 is a linear combination of V1, V2 and V3 or not? Okay. Till here you can argue, give the proper argument. Yes, this is a linear combination. Otherwise, the best the way it is generally we perform this one. No? We used to do this, that okay, you have a system of linear equation. Now solve this. If you want to solve it, let's solve. This is 1 4 1, okay, and 2 5 1, and 3 6 1. This is why, this is what it is. And right side is used to write the, like this augmented matrix 1 0 minus 1. This is your augmented matrix of this system of linear equation.
Sir.
Now perform other operations, all operations, and try to get alpha, beta values, gamma value. If it is exist, you can say yes, it is a linear combination. If it is not, then you can say it is a not linear combination. Very simple. Even if you are feeling the messy here, forget it and perform like this. Very neat and clean. Yes, it is happening there. And let's reserve this method to check that linearly independent and dependent. So let's discuss now the linearly independent dependent. The term is came now. The next even the next term is the linearly independent independent. Linearly independent and dependent. Okay. So here we have seen the last time independent and dependent. The same thing is going to be followed. That is exactly the same definition. What is the dependent means? Dependent means, let's say I'm saying the dependent here. First, I will discuss the, let's say, dependent case. So let's say I have a two vector v1 and v2. Okay, I will say these two vectors are dependent when v1 I am able to write a v1 as a some scalar time alpha time v2. This is what the last time we have seen. I am able to write v1 as a linear combination also. See the word I am saying, the definition itself. V1 as a linear combination of other vectors means here the v2, or even I am able to raise a v1 as alpha time v2. That is the meaning of saying to be v1 and v2 are dependent. Or let's say I am adding more now. We are doing R3 or more Rn. So let's say I am saying R4. Sorry, v3. Okay. So these three vectors I will say dependent if any of the linear combination. V1 I am able to write some alpha time v1 plus beta time v2, or v2 I am able to write some alpha time alpha prime v1, sorry v2, sorry v1 plus, oh sorry, here I am writing v2 plus v3, and here is v1 plus beta time beta prime of v3. Some any of the combination, or v3 I am able to write some plus some v1 and v2, any of them. If any of the is happening, I can say this is a linearly dependent. This is the meaning of, means any of the vector I can obtain by taking the linear combination of others. This is what is happening, right? Any of the vector is linear combination of rest of. This is what the meaning of linearly dependent. Okay. An independent case. So what is the independent then? Independent means I am not able to write. Means I am not able to write any of the vector as the linear combination of others. Means any of the vector. Let's say I am not able to write as a v1 as a linear combination of these two. So these three vectors are independent. Not only these two. Here is one by one. How we can say? Here is, let's say I have two vectors v1 and v2. I have two vectors. So here what it means that I am not able to write here a v1 as a some scalar time v2. If I have three vectors, let's say I have a three vector v1 and v2 and v3. So what it means that I am not able to write v1 as a linear combination of v2 plus some beta time v3. I'm not able to write. Then I can say these three vectors are linearly independent. Not only this one, this should happen also. Like v2 is also not able to write some alpha time v1 plus beta time v3. And V3 also, I'm not able to write some linear combination of alpha time V1 plus beta time V2. I'm not able to. All three should follow. Here is any of the will follow here. Then I can say yes, it is a dependent. But here, if all should not follow, then here is this all should be. V1 is not able to write as this one. V2 is not as this one. V3 is not as this one. All are independent to each other. This means all
Sir,
are
what
independent.
what if alpha and beta will be zero?
Alpha and beta will be zero. Huh. So
Sir,
here is
alpha
the
beta
second.
can
So
take any values, right? So if it is zero, then with the exception of this, alpha and beta will be zero. We don't write a linear combination, right? In this
so
alpha
yeah,
beta
so
form.
that is the proper definition. If you see what is the saying to be V1, V2, and V3, that is what the meaning is. I here is the meaning of it. Proper definition of saying to be three vectors are independent. Okay, independent if alpha time V1 plus beta time V2 plus gamma time V3 is equal to zero. If this system has only solution, what? Alpha is equal to 0, beta is equal to 0, and gamma is equal to 0. This is the proper definition of linearly independent. What it means that I can say three vectors are independent if I take a linear combination here. Okay, I take a linear combination here equal to 0, and I started solving. I got only alpha, beta, and gamma. The possible solution is only 0 solution. If it is there, then I can say yes, these three vectors are linearly independent. If it is any of the is non-zero, any of the non-zero, any of the non-zero, then it is dependent. Any any alpha or beta or any of the become non-zero, then it will become these three vectors are dependent. This is a this is a proper definition. Here, this is the meaning of it. These two are exactly saying to be the same meaning. If you are not able to understand it, so you can leave it. Let's discuss. Let's take this definition and let's solve some example. Then it will be more clear to you. So again, I am going to take vectors as 1, 2, 3, V1, V2 as 4, 5, 6, and V3 as 1, 1, and 1. Okay. I'm taking these three vectors. Okay. Now I want to check is this a linear combination of not means here sorry is this sorry this is a these three vectors are independent or dependent, that is the question now. Simultaneously, is this three vectors are dependent or independent? How we can check it? So simply let's take some alpha time v1 plus beta time v2 plus gamma time v3 is equal to 0. Take the linear combination equated to 0. Equated to 0 means here 0, 0, 0. Equated to 0 means these vectors are in three dimensions. So 0, 0, 0, 3 dimension 0. So here is alpha time 1, 2, 3 plus beta time 4, 5, 6 plus gamma time 1, 1, 1 equal to 0, 0, 0. Okay. This is alpha plus 4 beta plus gamma. Okay. And here is 2 alpha plus 5 beta plus gamma, and here is 3 alpha plus 6 beta plus gamma equal to 0, 0, 0. So here it will give alpha plus 4 beta plus gamma is equal to 0, and here is 2 alpha plus 5 beta plus gamma is equal to 0, and it is 3 alpha plus 6 beta plus gamma is equal to 0. You have this system of linear equation. Let's solve this system of linear equation. 1 4 1 and 2 5 1 3 6 1. Augmented matrix is 0 0. So here is all 0, so no need to write, right? You hope you remember that if it all are 0, so that means this is a homogeneous system of linear equation, and no need to write it. So let's proceed now. Let's solve this. So I have this one, here is 1, so I can do the operation row 2 minus 2 time row 1. So if you follow 1 4 1,
We can even
this
just do minus also. The column third will become 0.
mm-mm. Sorry,
We can
where
just simply R2 minus R1. We can do that. So the
R2
third column will become 0 in
third
R2.
become 0. Okay. So I will do here R2 minus R1. Uh,
That
you are
1 will
saying
become 2.
R2 minus R1. If you do it, we are not getting 0. No? Here is, it will be a different, not 0. Okay, let's do it here, this one, then I will see it. So here is 0, and here is 2 times 0, and this is 8 minus, this is minus 3, and this is minus 1. And again, I can simultaneously perform what is R3 minus 3 time R1. I'm also performing the simultaneously this operation. That means here, this will be here, no? 3 time minus 1. So this is 0, and this is 12, this is minus 6, and this is 3 and minus 2 here. Right? So this is now what I can say. See, these two are same, right? Only the twice number are there. So you can say R3 minus 2 time R1. You see it here. Sorry, 2 time R2. So this is a twice, right? This is just twice of it. So here is 1 4 1, and it is 0 minus 3 minus 1. And if you multiply uh, this row by 2 and then subtract the same numbers, you are getting the same numbers. So here that means here 0 0 0. This is what it is. Now you got this one. Now from here you are able to back to the system of linear equation. Means here what is this? Alpha plus 4 beta plus 1 is equal to 0, and here is minus 3 beta minus gamma is equal to 0. Hope you able to able to, from the matrix you are able to write the system, and from the system you are able to write the matrix. So this is what you will get. So from here what it means, that here is you can write, you can solve now easily, no? Here is, this means that 3, you can write this equation as a 3 beta, or let's say gamma is equal to, you can write minus 3 beta. And now you can substitute in the first equation alpha plus, here is 1 in place of 1, gamma is there, no? In place of beta, this is 4 beta, in place of gamma you can write 3 beta. So minus 3 beta is equal to 0. So here alpha plus beta is equal to 0. This will be alpha is equal to minus beta. So means here what is, you have infinitely many solutions. This tells you the system have infinitely many solutions. So you can give any value to beta, or mean to say your system is have a solution at least. The system have solution, right? You can give any value to beta. Here you can give beta is equal to 1, so that you can get gamma is equal to minus 3, and here it will be alpha is equal to minus 1. So all values you got. Means system have solution. That means what it tells you? It tells
Linearly
you
dependent.
the vectors are linearly dependent. You are not able to get 0 0 0 answer. You are able to get some non-zero value of alpha, beta, gamma. Okay. So this is what the meaning of it. Here is you are getting some non-zero value, alpha, beta, gamma. So what I said, if any of the non-zero become, then you can say this is a dependent. These three vectors are dependent. Okay. So the question is, can we get a independent vector? So I will give you another example to get the independent. So this is one method. Okay. So again, here is one method. You can follow, you can step, you can write like this, and then. Okay. This is one method. This is first method. The second method is you can take your vectors v1 as 1 2 3, v2 is 4 5 6, and v3 is 1 1 1. I want to check is this independent or not. So what you can do, you can write your vector as a row wise 1 2 3. This is the first vector. The second vector is 4 5 6. The third vector is 1 1 1. Okay, let's perform this. And while performing the operations, any of the row becomes 0. While performing the operations, any of the row becomes 0. So from there you can say itself these vectors are dependent. From there you can say these vectors are dependent.
Sir, if
Okay.
we write in row wise, like,
Mm-hmm.
or
Yes.
first we have done in the column wise.
Yeah, first one is we done column wise, but I didn't tell you. I didn't tell you, right. I am doing the column wise. I perform by the system of linear equation, and I didn't say that. See, I am the writing the vector as a column wise because you people get confused. Here is what is happening intrinsically. It is happening column wise, but I didn't tell you that I am doing it as a column wise. I am doing just a solving system of linear equation, as you know.
But
Okay,
in
so
second
but
method, you told the you if any of the row you will get zero, then it will be linearly dependent, right?
Then
Any of the
any
row.
of the, so while doing the perform operations, any of the row becomes 0, then it is a linearly dependent.
There is no need to give a reason, or like we have to write one line
Yeah, so
statement that this is.
one line is that, let me tell you the reason is that so even the, see, the thing is that here if you see there are so many things are there. That's why this is the first method. Okay, so don't say it is a column wise, just do the, I am solving the system of linear equation, I got non-zero solution, and so it is dependent. This is one method. The second method is, see, this is forming a proper square matrix. This is forming a proper square matrix. Okay. So it is a square matrix. So we can talk about the determinant of the matrix. So professor is
So you
didn't
are
talk
telling
you the
determinant
determinant.
will be zero, and it will dependent.
So it is dependent. I think it is there.
Yeah, yeah, sir.
Is okay. So if you
In one of
know
the
it
live
is,
in one of the live session, and in professor session, he also told us to the second method will be linearly dependent finding determinant. If is zero, then it is dependent. If not zero, then independent.
then independent. Yeah, if it, see, if it is a forming a proper square matrix, I am able to get the determinant of it. So you can say this, I have this matrix A. If the determinant of A is 0, then the vectors v1 v2 v3 are dependent. Okay, if determinant of A non-zero, then independent. Okay, then it is independent. Then it is independent. And also understand it by the determinant you understood. But also let me tell you that while performing the operation, I said no, any of the row becomes 0. What it means that? So let me tell you, then I will tell. Then let me do some operations here. So I am not doing any interchange here. I am just doing r uh, 2 minus 4 time r1. Okay, and I am doing also r3 minus r1. Two operations simultaneously I am doing. Okay, so how I am doing? Okay, here is 4 time r1, 4 time r1. Okay, so what I'm doing here is 1, 2, 3. I just wrote. Okay, now 4 time r1 and subtract 4 time r1 and then subtracting. So let's do that here. So this is become 0, and this is 8 minus 5. This is become minus 3, and this is 12 minus 8. This is minus 6. And this just here is doing I'm r3 minus r1. So this is 0, and this is minus 1, and this is minus 2. So now the next is, see it here what's happening. It is just twice of no. If you do r3, sorry, r2 divided by 3, if you see it here, 1, 2, 3, and 0, and this is minus 1, minus 2, 0, minus 1, minus 2. See, both are same. This is and this is are both are same. These two rows are same. So what it means that in the next operation, if you say it here is r2 minus or r3 minus r2, you will do. You will get here 1, 2, 3, 0, minus 1, minus 2, and here is 0, 0, 0 or r0. You got 0. So it means that these vectors are dependent. So from here, if you want to write, observe that while doing the operations, we got this fourth row is 0. So these vectors are dependent. Okay, this is proper argument and this is true. But are you able to understand why it is, what's happening here? The thing is happening here, you are doing something. See, this is your vector v1, right? And this is vector v2, and this is vector v3. Okay, these are the vectors. So what is happening? I am doing something so that, see, what is here is happening. I'm able here. What it means that here is you got 0, no? Here is you go v3. So while doing operation, this got 0. What it means that? That means I am able to write v3 as some linear combination of v1 plus some linear combination of v2. This is what it's happening, meaning this is what the meaning is there. This tells you that this R3 row, this the vector, this is your vector v3, this is vector v2, this is your vector v1. Same v1, v2 is there. See, I'm not doing any interchange, so same correspondent with there. Same correspondence is there, right? So this v3 is your this vector, v2 is this one, v1 is this one. What's happening here? Here, this tells you that v3 is some linear combination of v1 and v2. And if it is there, that is the definition we discussed just now. If it is there, then it is the dependent. Then they are dependent. And that is what is there. That is the argument you can say. So if you want to write, you can also write the proper argument as observe that the last row is 0. Last row is 0. So here is, so that means, or even that means, v3 is linear combination of v1 and v2. So they are dependent. By this argument, you can say it. Able to catch it? Not clear or mix up? More mix up is there? Just observe, slowly observe it. More things you will get. Okay, so whatever the doubts is coming in your mind, you're not able to distinguish between the linear combination dependent, please let me know what is doubt is in your thought it's coming. I'm not able to catch it, but maybe you can explain to me so that I can get, okay, this doubt you have. So if you are not understanding or any doubt you still have, please let me know. I will discuss that. So this is the meaning of linearly independent and dependent. This is how it is. So I till now I discussed the dependent till the second method I discussed, but I didn't give a single example of independent. So let's do one very quickly, one independent example. So let's say I have three vectors, v1 as 1 1 1, okay, v2 as 1 1 0, and v3 as 1 1 1. So I have this one. So is these vectors are independent or dependent? Very simple method. So either you can write like this vector wise. So let me write here. So here is 1 1 1. The second one is, this is my v1. This is the second vector is v2, 1 1 0. The third vector is, so sorry, here is 1 0 0, 1 0 0. This is my v2. This is my v3. And see, is this dependent or independent? So you can proceed some steps here. If you see it here, what's happening here? Row 2 minus row 1, row 3 minus row 1. So here it 1 1 1, and it is 0, and here is also 0, and here is -1. Subtract here. So this is 0, and this is -1, and this is -1. And the next step you can subtract it sorry, you can subtract it here to mm,
R3 is equals to R3 plus R1.
sorry,
Sir, we can also do R3 is equals to R3 plus R1.
R2 is equal to R3 plus R1. Even
R3,
I can
R3 is
uh, even I can interchange. Let me tell, if you able to catch it, then I'm not interchanging. Let's interchange it. What I am interchanging? Row 2 and row 3. So here is 1 1 1, and here is 0 -1 -1, and here is 0 0 -1. I just interchange slightly. So see what is there. You are not now perform or not able to perform any operation, so that here is any of the row becomes 0. All are doing after this. You are able to see this is a kind of upper triangular matrix, and here it tells you that here is below is 0, or any of the operation become, means if you do any further operation, none of the row becomes 0. This is the meaning of it. This is the meaning of. From here you can even say directly, from here observe that after further, even the further operation, we cannot get any of the row as 0. So these three vectors are independent. Or you can say from the determinant of the matrix. Or other way is that, or other way is that uh, by the system of linear equation. Very simple. So the best is either we could perform this way and say that you any of the after this, or from here observe that we cannot perform, or if you perform any of the further operation, none of the row become 0. So these three vectors are independent. From here it means very clear, right? Here is very clearly you can see I cannot make it any of the operation, any other further operation I will do, it will not become 0. Or simply alpha time v1 plus beta time v2 plus gamma time v3 equal to 0, and solve the system of linear equation. Very easily you can even solve. If you solve very quickly, here is going to be alpha time 1 1 1 plus beta time 1 1 0, and then gamma time 1 0 0 equal to 0 0 0. So here is alpha plus beta plus gamma. Here is alpha plus beta, and here is just alpha equal to 0 equal to 0 equal to 0. So That means what? Here is alpha is 0, so this implies beta is 0, and this implies gamma is 0, means after substituting all. So means here you got only 0, 0, 0 solution. You took the linear combination, but you got only 0 solution. So these vectors are independent. Okay, this is how you can easily do, or these are the. So by that way you can probably give the argument also, or by this way you can give. See, this is a very simple even. Sometimes this make easier, sometimes this make easier. So many times this will easier. Okay, so this is the meaning of independent and dependence. Let's discuss the last one, span. Even span is, see, lot more we discussed the linearly independent and dependent. Span dimension, maybe you can, because this span word and dimension, or maybe, sorry, span basis, we can discuss in the next session. Why? The reason is these three are more related. Basis, that the definition of basis is made by the span itself. But last time I will try to not spend more time on recalling. Okay, we discuss a lot with the examples on independent and dependent, but last time we'll not spend more time on recalling, so that we are able to cover span, basis, and dimension. Three terms are remaining now, so even it will be covered more, three sessions, I think. Yeah, even the linearly dependent is there. Span, member basis. Professor has solved more examples. See how he has rendered more examples. Uh, Here it is. 4 cross 3, 3 cross 4. See that these examples very clearly. Professor is discussing how you can solve this. See, these are just examples. He is solving how you can write the solutions. What is the meaning of it? What is the meaning of a span? This all he is discussing. 4 cross 3, 3 cross 4, 4 cross 4, or any dimension n cross n. So even you want, I can discuss the span very quickly a bit, and in the next session we also will spend time on span. So span is what? Again, I will relate to the last session. Span, I said, I started from there, how the, what is the meaning of span, or let's say I'm saying to be this one. Let's say last time I said, no, I have two vectors v1 and v2, and then I'm taking the linear combination. Let's say I have two vector 1 1 and another vector 1 0, and I took any linear combination, any of the linear. I'm taking just linear combination, general linear combination here. This is the linear combination. So this is a general linear combination. So I made it. I okay. This is a general linear combination. What I am saying, I am making a set. Yes, where whatever the values I can give any value, right? Alpha, beta, I can give any value to. I'm just saying any value. So here is belongs to 1, and I am fitting in this set. Just I'm fitting in this set. I'm just collecting all in this set. So this is called span. This, yes, this is a span of. add the word near span, just span along. So this is just a span of v1 and v2. This is just a span of v1 and v2. So if I will write in the set notation form, this is going to be alpha time 1 1 plus beta time 1 0, where alpha and beta belongs to. This is the last time I definition wrote. I did notation, definition, set definition. I just wrote. This is your span. I'm just collecting all possible linear combination of this set. That's all. This is the only. So this is for R2 we have seen. Let's do for R3 even. For the R3, I'm taking two vector V1 and V2. Even let's say V3. Even let's say V4 I'm taking. So let's say I'm taking 1 1 1. I'm another vector 1 0 1. The V, this is my V1. This is my V2. V3 is let's say 1 1 0. And another is 0 minus 1 0. Let's say I have this for vector side 2. This is R4, B4. So a span of these vectors is nothing but just linear combination. Alpha time V1 plus beta time V2 plus gamma time V3 plus delta time V4. Linear combination. Alpha, beta, gamma, delta belongs to R. So what it means that you can write here the linear combination and collect. So this is the collection of, right? Hope you know the set comprehensive. This is the meaning of I'm just collecting all possible linear combination. This is your style. We'll see more detail. We'll see how it is with the examples in the next session. So is this understandable? Even the span definition is understandable. We'll solve some more example in this span. On this span, span memberships we'll discuss. We have discussed it already. We will discuss with the R3 and R4. That's all it is. So if you recall your week 1, week 3 is nothing. So anyone wants to comment something, wants to say something? Understood? Any doubt? Any doubt from the lectures? Any doubt from
No,
the
sir.
notations? Okay, clear? Okay, that's all from my side. We'll see on the Friday. Okay, thanks. Thanks everyone. Thanks for joining and thanks for being interactive. The session to make this session as an interactive session. Okay.
Thank you, sir.